Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Master's Degree Programs, M.Sc. Mathematics with Applications in Computer Science, MACS Second Semester, MMT003 Algebra, Block-1 Group Theory, Unit 1 Basic Group Theory Review. 1.1 Introduction. With this unit you will be re-entering the world of abstract algebra. You will, of course, be delving deeper than you did in your undergraduate studies. For this purpose, in this unit we have put together those essential concepts that you have studied earlier, on which the first two blocks of this course will take you deeper. Accordingly, you will find a quick overview of groups, subgroups, cosets and Lagrange's theorem in Sec.1.2 to 1.4. Then, in Sec.1.5, we focus on normal subgroups and quotient groups. Following this, in Sec.1.6 we shall help you recall what a group homomorphism is, and the fundamental theorem of homomorphism for groups. If you need to relook any other algebraic concept from your undergraduate studies, please refer to the titles suggested in the course introduction. The unit is peppered with exercises. Doing them will help you engage more with the concepts concerned. So, please do not go further till you have done every exercise as you come to it. Let us now state the broad objectives of studying this unit. Objectives. After studying this unit, you should be able to recall what a group, a subgroup and a normal subgroup is. State, prove and apply Lagrange's theorem. State, prove and apply the fundamental theorem of homomorphism, and the other two isomorphism theorems, for groups, and state, prove and apply Cayley's theorem. 1.2 Groups. You would recall that a set is a well-defined collection of objects. So, for example, NZQR, C are sets of numbers that you will recognize. You may also recall that the empty set is denoted by or. Is it necessary that the objects in a set have some common property, or follow a pattern? For instance, is the collection of all living humans and all living insects in India on January 1, 2020, a set? This collection is well defined, and hence is a set. For the same reason, Indira Gandhi National Open University N7.5 is a set. Next, let us recall the definition and some properties of a binary operation. Definitions. 1. A binary operation on a set S is a function from times SS to S. If asterisk is a binary operation on S, we also say that S is closed with respect to asterisk. We usually denote S 21 by SS21. 2. A binary operation times SSS is called associative if SSSS. S is S. SS equals 32,13,21,321. 2. Commutative if S is SSSSS 2,11,221 equals, for example, addition and multiplication are associative and commutative binary operations on C, the set of complex numbers. Also, the intersection and union of the subsets of a non-empty set S are binary operations on S, the power set of S, that is, the set of all subsets of S. Can you see why? Think about it and do the following exercises. Now that you know what a set is and what a binary operation is, you would be ready to recall an hierarchy of algebraic objects. Definitions. 1. A semigroup is a pair S**, where S is a non-empty set and asterisk is an associative binary operation on S. 2. A monoid is a semigroup S**, such that S has an identity element with respect to asterisk. 3. A group is a monoid G**, such that every element of G has an inverse in GW. R. T. So, if we focus on the requirements for a group, we see that a group is a pair G**, where G is a non-empty set and asterisk is a binary operation on G for which the following properties hold. G1, asterisk is associative. G2, GE such that asterisk equals asterisks x6, GX, that is, G contains an identity element E with respect to asterisk, G3, for each GX such that x asterisk Y equals E equals Y asterisk X, that is, every element in G has an inverse in G with respect to asterisk. We denote the inverse of x by 1x minus. Before going further, here are some related remarks. Remarks 1. We often drop the operation while referring to a group, if the operation is understood. Here, we will also denote asterisk bar by. 2. If the operation is addition, 1 or minus will be denoted by minus a, and the identity will usually be denoted by 0.0. Similarly, the identity with respect to multiplication will usually be denoted by 1. So, by definition, Z plus is a group, but Z minus is not. Also, N plus is a semi-group, but neither a monoid nor a group. Similarly, the set of whole numbers, W is a monoid W, R, T, plus, but not a group. Let us look at another example of a group. 1.3 subgroups. You know that Z and R are groups with respect to the same binary operation, and ZR. This makes Z a subgroup of R, according to the definition below. Definitions. 1. A subset H of a group, G asterisk is called a subgroup of G denoted by less than or equal to GH, if H asterisk is a group. 2. If less than or equal to GH and GH, then H is called a proper subgroup of G. This is denoted by G, H less than or less than GH. 3. E is a subgroup of G, called the trivial subgroup of G, where E is the identity of GW, R, T, asterisk. For example, and the set of even permutations in Sn is a subgroup of S with n respect to O. However, Zn for n greater than 1 is not a subgroup of Z since Z and Z also, not every subset of a group is a subgroup. For instance, Nz, but n is not a subgroup of Z plus Y. So, we need some criteria to help us decide which subsets form subgroups. Do you recall the following criterion? Theorem 1, subgroup criterion. Let G be a group and H a non-empty subset of GH is a subgroup of G if a harp HP 1-. Let us use this criterion in some examples. Let us now quickly recall the properties involving operations on subgroups. We state them as a theorem. Theorem 2, let H and K be subgroups of a group. G then I equals KK. HH vertical bar HK. HK is a subgroup of G if equals HHK. K2, HK less than or equal to G. 3, less than or equal to GKH if KH or HK. Note that if G is a group W, R, T, plus, then HK should be seen as plus KH. Further, recall that if G is abelian then HK equals KH, so that HK less than or equal to G. 1.4 Lagrange's theorem. Let us begin this section with a definition. Definition: let H be a subgroup of a group G, and let Gx then the subsets of G equals vertical bar XHXHHH and equals HH vertical bar HXHX are called a left coset and a right coset, respectively, of H in G. The element X is called a representative of these cosets. Note that if the group operation is plus, then the cosets of H in G represented by X are plus equals plus HH vertical bar HXHX and plus equals plus HH vertical bar XHXH, respectively. Here are some important properties about cosets now, which we shall state for right cosets. They hold analogously for left cosets. Theorem 3, let G be a group, less than or equal to GH and G, X then I, XHX, 2, X equals HXHH, 3, Xi high HX1 equals minus. You can try and prove Theorem 3 yourself. Now let us recall how distinct cosets are formed. Theorem 4, let G be a group and less than or equal to GH. The relation on G defined by XY if Xi1- is an equivalence relation. The equivalence classes are the distinct right cosets of H in G. Thus, given any group G and its subgroup HXG, HGX equals. In fact, the distinct cosets partition G into sets of size OH, CE16. An immediate result that follows from Theorem 4 is the following. Corollary 1. If Hx and high are two right cosets of H in G, then high Hx equals or equals. Here are some exercises now. E16. Let less than or equal to GH. Show that there is a one-to-one correspondence between I, the elements of H, and those of any right or left coset of H in G. 2. The set of left cosets and the set of right cosets of H in G. E17. Find the distinct right cosets of A in 5S. 5E16, 2, tells us that the number of distinct cosets of a subgroup H in a group G is independent of whether we take all its left cosets or all its right cosets. Therefore, the following definition can be given. Definition: let H be a subgroup of a finite group G. The index of H in G is the number of distinct cosets of H in G and is denoted by vertical bar HG vertical bar. So, for example, n vertical bar n colon vertical bar ZZ equals n.2 vertical bar AS vertical bar 55 equals. Here is an important remark about cosets. Remark 3. For any less than or equal to GH and HX, GX, you know that XXH and XHX. So HXXH. However, it need not be true that does not equals XXH. H, for example, consider less than or equal to equals 3s21 H then equals 231, EH 31 and equals 321, E31 H so does not equal 31 H 31. Now, let us state the important theorem about finite groups that we had been aiming to do. This is due to the French mathematician Lagrange. He made significant contributions to the fields of analysis, number theory, and mechanics. His treatise, Théorie des fonctions analytiques, laid some of the foundations of group theory, anticipating the work done by the French mathematician Galois, 1811 to 1832. You will come across some of Galois' work in the last block of this course. Theorem 5, Lagrange, let H be a subgroup of a finite group. G then equals vertical bar HG vertical bar OHOG. That is, if a group is finite, then the order of a subgroup always divides the order of the group, and the index of a subgroup always divides the order of the group. As you can see, this result has so many consequences. For one, we can apply this to show that a group of prime order has no non-trivial proper subgroup. Now, let us recall what the order of an element of a group is. Definition: let G be a group and Gx the order of X, denoted by OX, is the order of the cyclic subgroup less than X greater than. Note that if less than greater than equals n vertical bar X vertical bar less than, then n is the least positive integer such that X n equals. If less than greater than X is an infinite subgroup of G, then X is said to be of infinite order, and then MX does not equal ZM and NMX does not equal X whenever M does not equal N. So, for instance, 221O equals N, Sn and N321O equals N, in, Sn greater than or equal to 3N. Also equals KOJO for IO in Q8. And, for any M, MZ is of infinite order. 1.5 Normal subgroups and quotient groups. Let us begin this section by considering remark 3 in the context of certain subgroups. Definition: a subgroup N of a group G is called a normal subgroup of GIF equals GXXN and X, and this is denoted by NG. Recall the following equivalent conditions: I, NGN NGGGG, minus 1 2, NGN NGGGG, minus 1 equals. Here, note that X equals X and N does not mean X equals I. And Y it just means that given NZ, NY such that X equals XZ. You can check that every subgroup of an abelian group is normal. However, the converse is not true, one example being Q8. You would also recall that every subgroup of index 2 in a group is a normal subgroup. Using this result, you know that N1 is N greater than. So, can you recall any subgroup that is not normal? For instance, you have seen in remark 3 that does not equal 21 31 31 21. So, 21. So, what is special about a normal subgroup? To answer this, we look at all the cosets of a normal subgroup, and remind you of the following theorem. Theorem 6. Let G be a group and HG. Let Hg be the set of all left cosets of H in G. Define multiplication on the elements of Hg by equals G, Xi high, XH. Then, Hg is a group. The multiplicative identity is A, that is, H, and the inverse of XH is Hx minus 1. The group defined in Theorem 6 is called the quotient group of G by H and is denoted by Hg. Note that I, taking all the right cosets of H in G, will give us an analogous group. 2. If G is a finite group, then no G/03. If H is not normal in G, then the cosets of H in G do not form a group. Why? 1.6 Group homomorphisms. Let us begin this section by considering the function sin f, 1, 1, s, fno sigma equals sigma minus. You know that f is a well-defined function. It also preserves the group operation, that is, s, f. Ff tau sigma equals tau sigma, and this property makes it a group homomorphism, as you would recall. More formally, F satisfies the following definition. Definition: let G11* and G22* be two groups, and phi G21 be a function. Phi is called a group homomorphism if y xx, y phi 1 equals phi 2 phi. If phi is bijective, it is called a group isomorphism. Further, the image of GGXX21 phi, im phi less than or equal to equals, and the kernel of phi, ker phi, equals 1 phi x equals EGX2, G, where 1 2 E is the identity in GW. R, T. Let us now recall some important theorems on homomorphisms and isomorphisms. The first such theorem is the basis on which the others depend. This is why it is called the fundamental theorem of homomorphism, FTH in short. Theorem 7, fundamental theorem of homomorphism. Let G and 1G be two groups and phi GG21 be a group homomorphism. Then erg phi minus img phi. Using theorem 7, example 12 tells us that SLGL 3R are in fact, on the same lines you can show that SLGL.2n NR are greater than or equal to. Similarly, applying theorem 7 to the signature homomorphism, you can see that as 2n1, 1 and n greater than or equal to minus. Now for the other two isomorphism theorems. Theorem 8, second isomorphism theorem, let H and K be subgroups of a group G, with K normal in G, then KHH and KHHK. Theorem 9, third isomorphism theorem, if H and K are normal subgroups of a group G and K less than or equal to H, then KHKGHG. Using these results, you can conclude, for example, that NZZZN or that 5Z153ZZ. We end this section with a result that tells us why permutation groups really form the basis of group theory. This theorem is due to the British mathematician Arthur Cayley, who proved it in 1854. We shall state it now and sketch its proof. Theorem 10, Cayley's theorem. Every group is isomorphic to a group of permutations. Outline of proof: let G be a group and GS be the group of permutations on the elements of G. For each GA define IG GFGGFA equals then GS car vertical bar F. And next, define F a F, GS GF equals a. Then, you can check that F is a well-defined group homomorphism, equals EFK and GSFM less than or equal to. Applying the fundamental theorem of homomorphism, we obtain the result. With this we come to the end of this rather long discussion for reviewing some of what you have studied about groups in your undergraduate studies. Let us end with summarizing the major points of this unit. 1.7 Summary. In this unit, we helped you recall the following points. 1. The definition and examples of a group and a subgroup. 2. The statement and applications of Lagrange's theorem. 3. The definition and examples of normal subgroups and quotient groups. 4. The definition and examples of group homomorphisms and isomorphisms. 5. The statement, proof and applications of the fundamental theorem of homomorphism. 6. The statement, proof and applications of Cayley's theorem for groups. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.